Okay, this is a video on using bond enthalpies to calculate delta H for a reaction. So one thing that is on the front of this note paper is a discussion on that breaking any kind of bond requires energy, so that the energy value would be positive, and any kind of bond formation releases energy, so that that energy release would be negative. And so there's a difference in energy values. When you break bonds, they're positive, and when you form bonds, they're negative. So the way these problems will look is you're given a reaction. Most of the time you're given a Lewis structure, or at least a partial Lewis structure as seen up here. You notice lone pairs are missing. You notice they didn't draw the 3 H's attached to the carbon, but for the most part they gave you a structure. And so the best way to go about doing this is to keep track of what bonds were broken and then what bonds were formed, and then we can apply the formula of enthalpy of bonds broken, or the sum of enthalpy of bonds broken minus the sum of enthalpies of bonds formed, to find delta H for this reaction. So if you look at the reaction that's given to you, the bonds that are broken will be on your reactant side, and so you're kind of going to compare your reactants to your products. And so in this reaction you can see that the hydrogen carbon bond was broken because a chlorine carbon bond formed. So one of my bonds that was broken was a carbon hydrogen bond, or a hydrogen carbon bond. It's the same thing. And then one of my bonds that was formed was a chlorine carbon bond, or a carbon chlorine bond. It doesn't matter which way you say it. So I broke the CH bond and I formed the CCl bond in this reaction, and then I also broke the chlorine-chlorine single bond, and I formed over here a hydrogen chlorine bond. So in this reaction we broke 2 bonds and we formed 2 bonds. And that's not always the case, but I mean, it's not always like you break 2 and you form 2, but in this case it just happens to be. So now I go to the chart. It's from your textbook, but it's on the front of your paper, and I don't have one with me, so I'm using the textbook, or otherwise I would show you. And so we go to the chart and we look up the enthalpy of the bond enthalpy for each of these bonds, and apply our formula, which is the sum of bonds broken minus bonds formed. And that will allow us to calculate a delta H. So we go to the chart and we look up a carbon-hydrogen bond, and we see that it is 413 kilojoules per mole. And we only have 1 carbon-hydrogen bond, so it's just going to be 413. If we had 2 carbon-hydrogen bonds, we'd have to double that number, and that's going to come up later in your packet. And then we look up CCl, it's a single bond, so there it is, 242 kilojoules. We do the same thing for the ones that we formed. A chlorine carbon bond, let's see, there it is, 328. And we are paying attention to whether these were single, double, or triple, because you'll notice in your chart they are broken down by single bonds and then multiple bonds, so be careful, but these ones are all single. And then the hydrogen chlorine bond is 431. So then I just apply my formula, the sum of the bonds broken minus the sum of the bonds formed. So I broke a 413 kilojoule bond and a 242 kilojoule bond. Okay, so those are my bonds that are broken, and then I'm going to subtract from that the sum of my bonds that are formed. And this becomes 655 kilojoules, and the other one becomes 759 kilojoules. And when we do the math, delta H for this reaction is negative 104 kilojoules. From that information, you'd be able to conclude that this reaction is exothermic because of the negative sign. And you can do this with any reaction, provided you have a way to look at the Lewis structures so that you can observe what bonds were broken and what bonds were formed, and provided that you have a table of bond enthalpies. So there's a couple extra practice problems that you can try, but the approach is the same way. Bonds broken minus bonds formed.